Now we will discuss the general procedure for obtaining pulse transfer function. Obtaining pulse transfer function. The general procedure for obtaining pulse transfer function. Now let us say we are having this diagram again, which is G of s and y of s. The output is y of s, this is x of s and x star of s with del t. For this we have y of s is equal to g of s into x star of s, and for this if you are applying starred Laplace transforms to this equation, then I will be having y star of s is equal to g star of s into x star of s. Then in terms of z domain, you can write this as y star of s. In terms of z domain, it is y of z and g of z into x of z. The similar thing if you are going with g of s, y of s and x of s. Now if you are having this, what is the relationship between y of s and x of s? You are having this one. Now if you are applying star Laplace transforms to this one, that is here in this diagram you doesn't have a sampler. You don't require any sampler. It means that it is a continuous time system and here it is a discrete time system. For example, if you are having this output, if you want to sample this output, it means that you require y star of s, which is nothing but g of s into x of s whole star. It means that you have to multiply these two, g into x of s whole star, or you can say that g x star of s, that is y star of s. Right. So therefore this is in starred Laplace transforms. Now if you are applying z domain, if you are writing this same equation in z domain, you can say that it is y of z is equal to g x of z. Previously in this case you are having y of z is equal to g of z into x of z. These two are two different z domains of g of t and x of t. Here you are multiplying these two functions g into x and then you are applying the z transforms. Right. Therefore there is a difference, a vast difference between these two transfer functions that we have obtained, relationships that we have obtained. This is the general procedure for obtaining pulse transfer function. Right. So we will see now different. You can also see the difference between these two in our immediate discussion. Here, what is the difference between g of z into x of z and g into x of z? Normally you can directly say that g of z into x of z is not equal to g into x of z. Okay, so this we will try to prove it while going for pulse transfer function for a cascaded system. Pulse transfer function for a cascaded system. Now what is a cascaded system here? For example, let me say I am having x of t, x star of t, del t, g of s, and again an output sampler with h of s and y of s. If I have these two signals in this system and I have one more system here which is having like this: x of t, g of s, h of s, and I have y of s here. This is x star of s, or I'll completely represent this with S domain functions, because only we are dealing with transfer functions. Therefore, I'll call this as x of s and x star of s. Now from this equation you can see that what is happening, what is the difference between these two: x of s del t, x star of s, g of s, and in between g of s and h of s we have one more sampler here, but here we doesn't have any sampler, and you have y of s here. So I would like to find out what is the difference between the transfer functions that are obtained in both these cases. Now let us see the first case. The first case, we can see that, for example, let me say we are having another function u of s here and u star of s here. Now from this diagram, diagram 1, you can say diagram 1, u of s is equal to g of s into x star of s. U of s is equal to g of s into x star of s. And from the same diagram we can say that y of s is equal to h of s into u star of s. H of s into u star of s. Now I want the relationship between y star of s and x star of s, which is required. Now from this equation you can say that u star of s is equal to g star s into x star of s, because here we are having two different Laplace transformed functions. G of s is the normal Laplace transformations, x of s is the starred Laplace transform. So when you are applying star Laplace transform to that, you are getting this one. Now if I replace u star of s here, y of s is equal to h of s into u star of s is g star of s into x star of s. Now to obtain a transfer function, what do you get? You, when you are applying starred Laplace transform to this equation, I have y star of s is equal to g star of s, or you can say we are having h of s g star of s x star of s whole star. For this, now h of s is the only normal Laplace transformed function, and the remaining two g of s and x of s are star transforms. So h of s can be automatically be starred as per the definition or derivation that we have proved in the previous session. So y of s, y star of s is equal to h star of s, g star of s, x star of s. So I will write down the equation here that y star of s is equal to g star of s, h star of s into x star of s. Now if you represent this in the z domain, in terms of z domain, you can say that this is y of z is equal to g of z, h of z, x of z, or y of z by x of z is equal to g of z, h of z. Right. So this is the transfer function that we have obtained when you are dealing with any. We have two different samplers, both are in synchronized in phase with each other, and then we are going to get y star of s is equal to g star h star into x star, and y of z by x of z, you get z of z into h of z. Now if you are going to discuss this transfer function, this block diagram, you can say that, for example, if you are having u of s here Right. Now this is a simple Laplace transformations. Y of s is equal to, and in fact you don't require U of s here because it is a cascaded element. We already know that G of s into H of s can be written without any hassle. G of s into H of s into x star of s. Right. Now I require only the star Laplace transforms here. Now if when I apply y star of s, you can say that here this is, for one simple simplification, you can say this is GH into S. GH of S. G of s, H of s can be written as GH of s. So I will write it as GH. You are multiplying G of s and H of s into x star of s. Now this becomes a single function. Two functions you are making it as a single function, GH of s into x star of s. Now y star of s, you can call this as GH star of s into x star of s. This is your y star of s. So I can say that y star of s is equal to GH star of s into x star of s. Now when you are applying z domain, you are representing this in z domain. I get y of z is equal to GH of z into x of z, or the pulse transfer function that we are going to get x of z. This is your pulse transfer function. You have GH of z. Now this is what we have found out. Now look at these two equations. This is one equation and this is the other equation. Y of z by x of z is G of z into H of z. Both in terms of block diagram, you can understand that G of s and H of s, the Y of s is equal to the output of this entire block diagram. Y of s is Gs into H of s. But you have sampler in between. Here you don't have sampler. When there is a sampler, you are having two different products of G of z and H of z. But when you don't have a sampler, you are having the z domain GH, the combination already done in the S domain, the product out over which you are applying the z domain. So GH of z. So eventually from these two derivations you can prove, you can say that from these two derivations you can say that G of z, H of z is not equal to G H of z, but G of s, H of s is equal to G H of s. So these two are holding good when this condition is happening. So this is pulse transfer function of cascaded elements. Right. Now let us say we are going with, we will take an example of this. Of this same, to illustratively explain what is the difference between G of z into H of z and GH of z. So let us say G of s is equal to 1 by s plus a and H of s is equal to 1 by s plus b. Right. So what is G of z? That is z transform of G of s, which is nothing but z by z minus e power minus at, and H of z is equal to z transform of H of s, which is equal to H of s is 1 by s plus b, and that equation you have z power minus bt. Now G of z into H of z. G of z into H of z gives you z square by z minus e power minus at. When you are multiplying these two, you have z minus e power minus bt. Now what is G into H of z? G into H of z is nothing but, when you are having this equation, G H of Z is equal to Z transform of G H of S, which is nothing but Z into G of S into H of S. Right. So what is the Z transform of G of S into S of H of S? I have here S plus A into 1 by S plus B. Right. So by applying partial fractions, you can say that 1 by S plus A, S plus B, you will have this as 1 by B minus A into 1 by S plus A minus 1 by S plus B. So I want the Z transform of 1 by S plus A, S plus B, or Z transform of 1 by B minus A into this one. So what do I get here? What do I get here? I get here 1 by B minus A into Z by Z minus E power minus AT minus Z by Z minus E power minus BT. This is G H of Z. Now from these two equations you can say that we are G H of Z. Now these are the two equations that we have derived. Now no way G H of Z and G of Z into H of Z, they are equal. They are not at all equal, because G of Z into H of Z, you have Z square by Z minus E power minus 8 into Z minus E power minus BT, and G H of Z you are having 1 by B minus A into Z by Z minus E power minus AT minus Z by Z minus E power minus BT. Therefore these two equations are not at all equal. Therefore we can conveniently say that G of Z into H of Z is not equal to G H of Z. But in the Laplace domain, you can say G of S, H of S is equal to G H of S. Right. So these two conditions are holding good. Therefore, for pulse transfer function of cascaded elements, we have seen with an illustrative diagram what is happening when you are using an sampler in between any two transfer functions, any two systems. Right. So with this in mind, we will try to discuss pulse transfer function for a closed loop control systems. Closed loop control systems. Pulse transfer function for a closed loop control systems. Now let us say I will consider an example here. Now this is our G of S, H of S, this is Y of S, let me say R of S, and negative feedback, and this is E of S, del T, and E star of S. Okay. Now I require the pulse transfer function of this closed loop system. So for this closed loop system, I can write equations for this. E of S is the sum of R of S minus H of S into Y of S. That is R of S minus H of S into Y of S. Right. So you are having Y of S there. Then what is Y of S? Is equal to G of S into E star of S. As for this relationship, Y of S is equal to G of S into E star of S. Now I require Y star of S by R star of S. Now we require the relationship between Y star of S and R star of S. Right. So the relationship, what is the relationship between Y star of S and R star of S? That is what we require. So I apply start the Laplace transform to this equation when I am applying star Laplace transform to E star of S, I get E star of S is equal to R star of S minus H of S into Y of S. These are two different functions which are multiplied in the S domain. Therefore, they can combinedly called as H Y of S star. H Y of S star. Or you can also do it E of S is equal to R of S minus H of S into, now you have Y of S here. Y of S, if you replace it here, you will get G of S into E star of S. Right. So this is equation 1 and equation 2 here. Now if you substitute equation 2 in equation 1, in this place you have E of S is equal to R of S minus H of S into Y of S is G of S E star of S. Now applying starred Laplace transforms to this equation number 3, we will get E star of S is equal to R star of S minus G of S into H of S is nothing but GH star of S into E star of S. Right. So what is E star of S? When you are bringing this term E star of S term to the left hand side, you have 1 plus GH E star of S into 1 plus GH star of S is equal to R star of S. Right. And this equation gives us, this equation 4 gives us E star of S is equal to R star of S by 1 plus GH star of S. Now this is equation 5. Now if you replace equation 5 and apply star transforms to Y star of S, we have Y star of S is equal to G star of S into E star of S. Right. So if this is equation 6, for this equation when you are applying star transforms, Y of S, Y star of S, G of S is G star of S and E star of S is again E star of S. Therefore, in this, if I replace this with E star of S and this equation 5 is replaced here, I have Y star of S is equal to G star of S into R star of S by 1 plus GH star of S. Now when you are obtaining or applying Z domain, Z transformations to this transfer function, I have Y of Z, R of Z can be brought down, R of Z is nothing but G of Z by 1 plus G H of Z. Now this is the pulse transfer function of closed loop control systems. Therefore, with this in mind, you have different types of configurations that we are going to have in this closed loop transfer function. You can also have a better picture when we will try to see one more diagram here. For example, this is R of S, G of S, H of S, a positive and negative. Here you have a negative feedback. You have E of S, E star of S, G of S, C of S, right? And you can say this is C star of S, right? Therefore, for this equation, if you want to obtain C of Z, which is the output, by R of Z. What is C of Z by R of Z? Which is the pulse transfer function. Now for this equation, you can say, you can write equations for this. C of S is equal to G of S into E star of S. And similarly, what is E of S? E of S is equal to R of S minus H of S, C of S. Right. Now when I replace, instead of C of S here, I have R of S minus H of S, G of S, E star of S. This is E of S. Okay. Now when you apply star Laplace transform to this equation, you have E star of S is equal to R star of S minus GH of S star E star of S. Right, because these are two different functions, I have combined this into a single function and applied the star Laplace transform there. Now E star of S, I have this as, coming into this equation, you can say E star of S is equal to R star of S by 1 plus GH star of S. From this equation, I can get this equation. Now when you are having this, you can substitute here, and you can say when you are applying star Laplace transforms to this one, I have C star of S is equal to G star of S into E star of S. For this first equation, you can apply star Laplace transforms and you can obtain this equation. Therefore, C star of S is equal to G star of S into E star of S. You can replace this equation, R star of S by 1 plus GH star of S. Right. So with this equations, when you are obtaining, that is the star Laplace transforms, right? When you are obtaining Z domain, when you are representing this entire equation in Z domain, you get this as C of Z is equal to G of Z by 1 plus GH of Z into R of Z. So this is your output. C of Z is equal to G of Z by 1 plus GH of Z into R of Z. So these are different types of configurations that we have, and if the same, for the same equation, if we can say that this is connected here, the equation of this can be changed. Now this is one more configuration here that we can discuss, and here again C of S is equal to G of S into E star of S. Now this is a different configuration. When in the previous case we have taken output from C of S, now the output is taken from C star of S. Therefore, what is E of S? E of S is equal to R of S minus H of S into C star of S. H of S into C star of S. Now when I apply star Laplace transform to this equation, I will have E star of S is equal to R star of S minus H star of S into C star of S. Right. So now when I apply star transforms to this equation, I have C star of S is equal to G star of S into E star of S. Right. Now when we can easily substitute E star of S in this equation, where I get C star of S is equal to G star of S into, what is E star of S? We have here R star of S minus H star of S into C star of S. That is, we are substituting E star of S here. That is, this entire part you have replaced it here instead of here. Right. So E star of S is this one. So what is C star of S? We have C star of S is equal to G star S R star S minus G star S H star S into C star S. Now you have C star of S and C star of S. You have need to sign here. When you are taking it to the left hand side, I will have C star of S is equal to G star of S R star of S by 1 plus G star of S into H star of S. Now when you are applying Z then to the Z domain or representing the star transforms in Z domain, I will have C of Z. This is C star of S is C of Z, which is equal to G of Z. G star of S is G of Z into R of Z by 1 plus G of Z into H of Z. So you can see that when there is a small change, in the previous case you have GH of Z. Here G of Z into H of Z. The same transfer function, you are having it in this form. Right. So you have various different types of configurations that we can obtain and work out on various configurations, because a block diagram, any system can be of different forms. Therefore outputs, the samplers can be placed anywhere in the system. Therefore you will have to apply star Laplace transforms and then convert back to Z domain, so that you will get the pulse transfer functions of any type of closed loop control systems.